Welcome to UXL, where you can learn new skills anytime and anywhere. Visit uxl.com to explore our full course selection. This lesson is part of a larger course. Check the video description below for a link to the full course where you can enroll. If you enjoy our content, please like and subscribe. For your convenience, the course cover displayed on your screen provides the complete course title and lesson title. Let's proceed with the lesson. Lesson: Nash Equilibrium and its importance. Nash equilibrium is a fundamental concept in game theory that has profound implications for strategic decision-making in economics. Named after the mathematician John Nash, who first introduced the concept in his 1950 dissertation, Nash equilibrium occurs when players in a strategic game choose strategies that are optimal given the strategies chosen by other players. In such a state, no player can benefit by unilaterally changing their strategy. Understanding Nash equilibrium is crucial for analyzing competitive situations where the outcome for each participant depends on the choices of others. At its core, the Nash equilibrium provides a solution concept for non-cooperative games involving two or more players. Each player's strategy is assumed to maximize their payoffs, given the strategies of all other players. This mutual best response condition ensures that once an equilibrium is reached, no single player has the incentive to deviate, as doing so would not result in a better outcome for them. Consider a simple example of Nash equilibrium: the prisoner's dilemma. In this classic game, two criminals are arrested and interrogated separately. Each has the option to either betray the other by testifying or to remain silent. If both betray each other, they receive moderate sentences. If one betrays while the other remains silent, the betrayer goes free while the other gets a heavy sentence. If both remain silent, they get light sentences. The Nash equilibrium in this scenario is for both prisoners to betray each other, as defecting is the best response to the other's strategy, despite the fact that mutual cooperation would lead to a better collective outcome. The importance of Nash equilibrium extends beyond theoretical models and has real-world applications in various economic contexts. For instance, in oligopolistic markets where a few firms dominate, companies must decide on pricing strategies while considering the potential reactions of their competitors. In such markets, firms often reach a Nash equilibrium where each sets a price that maximizes its profit given the prices set by others. Deviating from this equilibrium could lead to a price war, eroding profits for all firms involved. Another significant application of Nash equilibrium is in auction design. In particular, the concept is used to predict bidding strategies and outcomes in various auction formats. For example, in a first-price sealed bid auction, each bidder submits a bid without knowing the other's bids, and the highest bidder wins but pays their bid amount. The Nash equilibrium bidding strategy in this auction involves shading bids below the bidder's true valuation to avoid the winner's curse, where the winner overpays due to overly aggressive bidding. Nash equilibrium also plays a crucial role in public goods provision. Public goods are characterized by non-excludability and non-rivalry, meaning that one person's consumption of the good does not reduce its availability to others, and it is not possible to exclude anyone from using it. Examples include clean air, national defense, and public parks. Game theory helps economists understand how individuals might contribute to the provision of public goods. The Nash equilibrium in this context often reveals the free rider problem, where individuals have an incentive to refrain from contributing, hoping others will bear the cost. This understanding informs policy measures aimed at encouraging cooperative behavior, such as taxation and subsidies. The concept of Nash equilibrium extends to international trade negotiations, where countries strategize to maximize their economic benefits. Trade agreements often reach a Nash equilibrium where each country's strategy is optimal given the strategies of the others. For example, two countries may agree on specific tariff reductions that are mutually beneficial. Deviating from the agreement could lead to retaliatory measures, resulting in a suboptimal outcome for both. In financial markets, Nash equilibrium can explain the behavior of investors during periods of market uncertainty. For instance, during a financial crisis, investors must decide whether to hold or sell their assets. The Nash equilibrium in such a scenario might involve all investors selling their assets to minimize losses, even though this collective panic selling can exacerbate the crisis. Understanding this equilibrium helps policymakers design interventions to stabilize markets, such as providing liquidity or guaranteeing asset values. The theoretical foundation of Nash equilibrium is supported by empirical evidence from experimental economics. Laboratory experiments involving human subjects playing strategic games have consistently shown that individuals tend to converge towards Nash equilibrium strategies. These findings validate the predictive power of the equilibrium concept and its relevance to real-world decision-making. Despite its wide-ranging applications and robustness, Nash equilibrium is not without limitations. One criticism is that it assumes rationality and complete information, which may not always hold in practice. Players may have bounded rationality, where cognitive limitations prevent them from identifying the optimal strategy. Additionally, in many real-world scenarios, players may not have complete information about others' payoffs or strategies. These factors can lead to deviations from Nash equilibrium predictions. Moreover, some games have multiple Nash equilibria, making it challenging to predict which equilibrium will be selected. Coordination games, where players benefit from making the same choices, often exhibit this characteristic. For example, in a traffic coordination game, where drivers must choose to drive on the left or right side of the road, both and are Nash equilibria. The challenge lies in achieving the same equilibrium without communication, highlighting the complexity of strategic interactions. In conclusion, Nash equilibrium is a cornerstone of game theory and a vital tool for understanding strategic decision-making in economics. Its applications span various domains, including market competition, auction design, public goods provision, international trade, and financial markets. While the concept assumes rationality and complete information, its empirical validation and practical relevance underscore its significance. By providing a framework to analyze and predict strategic behavior, Nash equilibrium enables economists and policymakers to design better interventions and foster cooperative outcomes in complex economic environments. This concludes the lesson. We trust you found this video informative and engaging. To enroll in the complete course, please use the link provided in the description below. At UExcel, we are committed to your learning journey. Each course offers a certificate of completion, online support, and downloadable resource files to enhance your experience. If you found our content valuable, we invite you to like this video and subscribe to our channel. Thank you for joining us, and we look forward to supporting your continued pursuit of knowledge.